Pick up a piece of copper. Go ahead, hold it. It's cool, heavy, quiet. Seems like it's just sitting there, doing nothing. But I'm going to let you in on something. Inside that metal right now, there is an absolute riot going on. Silent, invisible, completely insane. And it runs on one rule, just one. That explains basically everything about electricity. Here it is, like Pell's like. Unlike attracts. That's the whole game. From that one principle, that one gorgeous, mysterious rule. You can reconstruct the entire electrical universe. Let's go inside. Everything is made of atoms. Now forget the neat little solar system diagram they showed you in school. Think of it more like a crowded party. At the center, you've got protons, positive charge. Circling way out at the edge, you've got electrons, negative charge. And because of that rule, the protons and electrons are crazy about each other. They pull together. But two protons, two electrons, they push apart, hard. Here's the first thing that should stop you cold. Nobody, and I mean nobody, knows what charge actually is. We know what it does. We've named its behaviors. Positive, negative, attract, repel. But the deep down why of it, that's still a mystery. It's just a rule the universe plays by. An axiom. Take it or leave it. Now back to that copper. In some materials, rubber, glass, every electron is locked to its atom. Can't go anywhere. Those are insulators. But copper is different. In copper, the outermost electrons are basically freelancers. They don't belong to any one atom. They just drift, wander, float through the whole metal like people milling around a concert, no assigned seats. We call them free electrons. That's why copper conducts. It's got this whole sea of electrons just waiting for a reason to move. Wrap copper in rubber, and you've got a channel of wanderers surrounded by prisoners. Electricity flows through the middle, can't escape through the sides. That is literally the trick inside every single wire in your walls. Elegant, right? Now for these electrons to flow, to become electricity, they need a push. Think of a pipe full of water, perfectly level. Nothing happens. Now, tilt it. The water rushes from the high end to the low end. That tilt, that pressure difference, that's voltage, electrical tilt. A battery creates that tilt using chemistry. It physically pumps electrons, crowds them up at the negative terminal, drains them from the positive. You've got a surplus on one end, a deficit on the other. Connect them with a wire and boom, the electrons rush from crowded to scarce. That collective rush is electric current. That's it. That's electricity. But the flow isn't smooth. As electrons drift through the wire, they're constantly bumping into the fixed atoms of the metal. Every collision shakes those atoms, makes them vibrate faster. And what's faster atomic vibration? That's heat. So wires carrying current warm up. We call this resistance. The atomic friction of electrons pushing through the lattice. A thin wire has more resistance than a thick one. Same reason it's harder to drink a milkshake through a cocktail straw than through a garden hose. Now take that idea and run with it. What if you deliberately used a wire with really high resistance, like the tungsten filament in an old light bulb? You force current through it. The collisions get so violent the atoms don't just warm up. They glow white hot. They throw off light. A light bulb is just a wire that's bad at its job. Gloriously bad at its job. Here's something that should scramble your brain a little. We think of electricity as this modern human thing, a technology. It's not. All of chemistry is electricity. When atoms bond into molecules, that's electrons finding new dance partners based on attraction and repulsion. When wood burns, electrons are jumping to more comfortable arrangements. When your nerves fire, a wave of electrical imbalance races down a biological wire straight to your brain. You are not a creature that uses electricity. You are electricity. Walking, talking, pattern of charge balance. And we've been calling it biology. Now hold two ideas at once. First, the electrical force is almost incomprehensibly strong. About 10 quintillion times stronger than gravity. That number means nothing to a human brain. So let me give you this. If you and the person next to you each had just 1% more electrons than protons in your bodies, a tiny 1% imbalance, the repulsive force between you would be enough to lift the entire Earth, the entire planet. Second idea, you feel none of this, not even a whisper. Why? Because in every piece of matter around you, positive and negative charges are balanced with almost perfect precision. The titanic forces are all canceling out, leaving just the faintest residue. And that residue is gravity. The everyday solidity of the world is a flawless standoff between unimaginable powers that have agreed to a draw. This is why the ancients only ever stumbled across two weird electrical curiosities, that rubbed amber attracted straw, and that a rock from a place called magnesia attracted iron. They were poking at the fundamental glue of the cosmos without any idea what they had. The balance was too perfect to see. Now here's where it gets beautiful. Electricity has a twin. Magnetism. Seems totally different. One gives you shocks, one holds stuff to your fridge. But they're the same thing wearing two different coats. Run electrons through a wire, you create a circular magnetic field around it. That's not a metaphor. Move a compass near a live wire and the needle physically twitches. Coil the wire, the field gets stronger. Wrap it around iron, you've got an electromagnet. Magnetism you can switch on and off with the flip of a switch. And it runs the other way too. Move a magnet near a wire and you push electrons through that wire. No battery, no chemistry, just motion. This is induction and is the secret behind every power plant on Earth. At a dam, at a steam plant, at a wind farm, you're spinning a giant magnet inside a giant coil of wire. Motion turns into current. The kinetic energy of a river hundreds of miles away becomes the light you're reading by right now. That is not a metaphor. That is literally what's happening. James Clerk Maxwell tied all this together in the 1860s. He worked out that a changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. They can sustain each other, leapfrog through empty space. He calculated the speed of this traveling disturbance and got a very familiar number, the speed of light. The conclusion was inescapable. Light is an electromagnetic wave. Radio signals, X-rays, the heat coming off a fire, the colors on your screen, all the same phenomenon, just wiggling at different frequencies. We live inside an electromagnetic ocean and we can see only the thinnest sliver of it. Let this one really land. You have never touched anything, not once in your life. When your hand rests on a table, the electrons in your skin approach the electrons in the table's surface. Same charge. They push apart. The sensation of solid contact, that resistance you feel, is the force of that repulsion acting across a gap of pure emptiness. Matter feels solid, not because atoms are hard little balls. It feels solid because the electrical force fields around them will not give ground. You are being held up right now by a continuous, flawless electrical argument between your feet and the floor. Even a nuclear explosion is at its heart an electrical event. In a uranium nucleus, 92 protons are crammed together. Their mutual repulsion is enormous. Held in check only by the strong nuclear force acting at very short range. Split the nucleus and you blow that lid off. The two pieces, both positively charged, fly apart with every ounce of electrical fury that had been bottled up. The explosion is a sudden, catastrophic victory of electromagnetism. Capture it. We've learned to describe this force with extraordinary precision. We can predict it, harness it,